Hello and welcome to the second session of the course, the Power Plant System Engineering. So till now, nobody has joined. So I'm going to the presentation. Meanwhile, anybody can join. Okay, so let me share my presentation. Yeah, somebody is there. Yeah, hello and welcome to the second session of the course, Power Plant System Engineering. So let me go to the slide. Meanwhile, if you are having any doubt, so we can take that. Okay. So as the time is already there, let me go to the slides first. And my people are there. Alright, so in between, if anybody want to join, they can join. Let me go to the slides. Please let me know whether my pen is working or not, or my voice is okay or not. Okay. I will summarize the thing and I will solve the classroom questions and the assignment questions and try to take your doubt in the session. Yes, so I hope my slide is visible. All right, so this is V2, sorry. Okay, so yeah, here we go. Let me take the pen. Okay, so in this week, the topics which are covered are the vapor power plants. All right, vapor power plants, performance indicators, thermodynamic cycle, Carnot cycle and its limitations, power plant design considerations, modeling of the Rankine cycle, ideal Rankine cycle, effects of boiler and the condenser pressure. Here I will try to focus again, and the irreversibility and the losses. Here we will try to get the concept of the turbine and compressor, turbine and pump isentropic efficiencies. Okay, then I will solve the assignment two questions. The aim of the session would be the same, to summarize the things, to discuss the doubts occurred, and to solve the assignments and classroom problems. Okay, yeah. So, like here, we can go. So, the first session we have started with the vapor power plants. Okay, and the Carnot efficiency of a engine which is connected to two sources, like one is heat source which is at high temperature TH and one is heat sinks. This is heat engine and one is heat sink which is at lower temperature TC and it is producing some work W net. Okay, somebody is there. Take it. All right, and there is some network. So from the heat source, the heat is coming to heat engine Q in, and it is rejected to the heat sink Q out. Okay, so As the Carnot efficiency we have learned in last class, it would be 1 minus the lower temperature, the basically this is source and this is sink. Source would be at higher temperature. So it is 1 minus sink temperature by the source temperature, 1 minus Th by Tc. However, in actual, it is defined as the ratio of the network output divided by the heat supplied, which is Q in. Okay, and this W net will be the difference of the Q in minus Q in and Q out. Okay, so next, the performance in indicators. There you have learned about the efficiency ratio. Efficiency ratio is nothing but it is the ratio of the actual thermal efficiency to the ideal thermal efficiency. Okay, and here the ideal thermal efficiency is the Carnot efficiency, and this actual thermal efficiency is the ratio of the net work done divided by the heat supplied. Then the work ratio we have come across. The work ratio was the net work done divided by the turbine work. Okay, these work. Let me take the cycle first. So this is the Rankine cycle, and it is between the two pressures. Let me draw two pressure line first. This is temperature and this is entropy. Okay, so let me take the processes. Like this is the condenser pressure P1, this is lower pressure, and this is the okay. Let me take it pressure P2, and this is my pressure P1. This is the boiler pressure, and this is the condenser pressure. Okay, so the Rankine cycle will be like this. Okay, this is pump work, and it would be something. It would be like this. So this is the point one is the turbine entry, two is turbine exit, three is the condenser exit, and four is the boiler or boiler entry. Okay, so while expanding from point one to point two, we will receive the turbine work WT, and this is point 4 to point 1 is the heat supplied in the boiler Q in. 2 to 3 it is the heat rejected or heat out in the condenser, and 3 to 4 it is the pump work. So here the net work is my turbine work minus the pump work. Okay, so this is the terminology, and based on this the work ratio is defined as the ratio of the okay, this is capital T actually, the turbine work capital T. Okay, so work ratio is the ratio of the net work done divided by the turbine work. Similar to this, one another terminology is back work ratio is defined, which is the ratio of the pump work divided by the turbine work. Okay, and based on this, we can say that summation of work ratio plus back work ratio would be 1. Okay, so these are this complementary. Next, we have defined the specific steam consumption SSE. It is basically the steam consumed to generate the 1 kilowatt of uh, network, and it is defined the reciprocal of the network. And here the WNet is having the unit of the kilojoule per kg. Okay, so what would be the unit of SSC? It would be the kg per kilojoule, and to convert it into the kg per kilowatt hour, we have to multiply by the 3600. So it is the final thing. The SSC would be the 3600 by WNet, and the unit would be kg per kilowatt hour. Okay, because in kg per kilojoule or kg per kg watt into second, the value would be very less. So generally we calculate it in terms of kg per kilowatt hour. Okay, so I assume that all these things you have come across. Next thing is the heat rate. Heat rate I will write here. Basically, the heat rate is the heat supplied per kilowatt hour of network done. Okay, so this is the heat rate. So this efficiency ratio, work ratio, back work ratio, heat rate, and this specific steam consumption. These are the performance parameters. Based on that, we evaluate the performance of any uh, vapor power plant or the Rankine cycle power plant. Okay, so next you have learned the steady flow steady flow calculations here, like uh, steady flow calculations. Okay, the thermodynamic analysis. Like, let me make the Rankine cycle like this. Okay, I'm just making the block diagrams. This is my boiler, this is turbine, this is condenser, and this is pump. Okay, so what we will do, we we pump the water to the boiler where it is getting heated in the boiler and converted into the steam, then it expanded into in the turbine to produce the turbine work, then it is condensed to the saturated water. Okay, and different works we get, like, let me write, this is point 1, this is point 2, this is point 3, and this is point 4. The same thing we can draw on the TS diagram. Okay, so like this is the TS diagram, and let me take the another color pen. This is point 1 to 2, point 1 to point 2. This shows the expansion of the steam inside the turbine, and point 2 to point 3, it rejected heat in the condenser, then point 3 to point 4, the pressure work is the pump work is supplied to increase the pressure from condenser pressure to the boiler pressure, like this is the boiler pressure, and then it is heated in the boiler at the boiler pressure. So these are the four processes which we uh, have in the Rankine cycle or vapor power plants. The work which we get here in the turbine, we get the turbine work output WT. This work we can also show here, WT, and in the boiler, the heat supplied, Q in, we can write here, we are supplying the heat, Q in. In the condenser, some heat is rejected, we will say Q out or QR. here is Q out, and here we have to supply the pump work to increase the pressure from the condenser pressure to the boiler pressure. So this is WP, here it is WP. So the thermodynamic analysis is nothing but we have to determine the enthalpy at those 4 points. Okay, and if we get the values of this enthalpy, we would be able to calculate all the work done, the heat added, and the different efficiencies. Okay, so if you look at point 1 to 2, then suppose the enthalpy at point 1 is H1, enthalpy at point 2 is H2, enthalpy at point 3 is H3, and enthalpy at point 4 is H4. So what will be the work done? So in the okay, so work done in the turbine would be simply H1 minus H2, because at point 1 the steam is having higher enthalpy, and at point 2 the steam is having lower enthalpy. Okay, and it would have the unit per kg, like kilojoule per kg. So these are the specific thing which the value would be given per kg. Okay, and per kg means per kg of steam flow rate. Then this Q out in the condenser, it would be H2 minus H3. Then pump work would be H4 minus H3. Then the heat added in the boiler, Q in, would be the H1 minus H4. So these are the four things: the heat, the work done in the turbine, the work supplied to the pump, the heat rejected, and heat added. So we have to determine these four things when we have to assess a vapor power cycle or a Rankine cycle. Then next we have learned the Carnot analysis and its limitations. So it is simple that we cannot adopt. Okay, let me take. Yeah. So here we have seen that we cannot adopt the Carnot uh, cycle in the vapor power plants. The reasons are very simple. Like it is very difficult to handle the vapor and liquid mixtures. It is difficult, very difficult to compress it, and also in that case the pump work is very high. This is the reason because we have to modify the Carnot cycle and the more and to go for the Rankine cycle. Uh, because in the Rankine cycle, the work ratio for the Rankine cycle is more than the work ratio of the Carnot cycle. And we have to do here with the work ratio only, because if we adopt the Carnot cycle, the work output would be very less, because in that case the pump work is very high. Okay, so then we have learned different considerations, okay, while designing the power plant. So, and I will not waste much time on that. Only one highlight is there. We should prefer the design, should prefer the plant design where the pump work WP would be least. So these things we have to keep in mind. Next, yeah. Next, I will start with this problem. Okay. So here, this problem, although it is solved in the uh, classroom, but my aim is to show you how to see the values from the Steam table, and because of that, I have pasted the Steam table at the required pressures here. Like the two important pressure here is given like 0.05 bar, and the Steam table which I have pasted here is in mega pascal. So 0.04 4 bar would be 0.004 megapascal, and this 35 bar would be the 3.5 megapascal. Okay, so the things which have asked in this problem are we have to calculate the heat and work transfers, cycle efficiencies, work ratio, and specific fuel consumption of a Carnot cycle operating between 35 and 0.04 bar. So this is the example of the Carnot cycle, and here we will see that how much the pump work we will get here. Okay, and the work ratio would be also high. In the next problem, which would be based on the Rankine cycle, there we will see the work ratio would be significantly high than the this Carnot when we adopt the Carnot cycle here. Okay, so we will start. Let me add some slides to it. Okay, so yeah, here we will solve this. First, I will make the cycle here. Let me draw it here. Okay, so these two axes are temperature and the entropy, and this is the vapor dome. Okay, so sorry about my drawing. It is should be like this. It is like this. It should be better. Okay, then let me mark two pressures here. This is the higher pressure and this is lower pressure, and the saturated temperature against these pressures I will write here. Okay, so what is Carnot cycle? So Carnot cycle is having two isentropic and two isothermal processes. So it would be inside this dome only, because at the constant pressure line would be like this. So the temperature would not be constant there. Okay, let me take another. Yeah, so constant pressure lines would be like this. So outside the dome, the temperature would not be constant. So Carnot cycle would be restricted to inside this dome only. Okay, so the pressure would be like the processes would be like this. Okay, so here let me write point 1 is the inlet of the turbine, point 2 is the outlet of the turbine, 2 to 3 is the condensing, and 3 to 4 is the pump work. Okay, so these are the things. Let me write that this is the pressure P1, okay, and this is the pressure P2. So here I won't make this plot very messy, but let me write the values here from the different pair. This is the turbine work, this is the pump work, WP. Okay, this is the heat out, and this is the heat in the boiler. So these four things I want to plot here only. Meanwhile, if you are having any doubt, you can stop me, and then we can discuss on that. Okay, so let me write the value of these pressures first. So it is given that pressure P1 is 35 bar, or it would be 3.5 megapascal. The pressure P2 is 0.04 bar, or it would be the 0.004 megapascal. Okay, and against these pressors we can see the saturated temperature. Okay, so this row is representing the values for the pressure P2, which is 0.004 bar, and this row representing the values for the 3.5 bar. Okay, so here first column is the saturated temperature, second one is the specific volume at this line, the saturated liquid line. Vg is the specific volume at the saturated vapor line. UF is the internal energy for the fluid or liquid, and Ug is the internal energy for the gas. Here the HF and Hg are the enthalpy for the uh, liquid and the vapor respectively, and HFG is the latent heat. Okay, and it would be the difference of Hg minus Hf. Similarly, SF, Sg, and SFG are the entropies at the liquid, gaseous, and this would be the difference of that SFG. Okay, so let me write the values here. First, the saturated saturation temperature Tsat at zero point 0.1. It is given 242.557 degrees centigrade, and saturated temperature at zero point 0.2, it is 28.96 degrees centigrade. The values we can find from here, from the first column only. Okay. Okay, so this value in the Kelvin, this value will comes out to be 515.5 Kelvin. I am leaving the extra terms after the decimal point, and this value would be with 301.96 Kelvin. Okay, so these are the values, and now I will write the enthalpy values. So here we can see that at this point 1 is the saturated vapor line. Okay, and at the pressure P1. So at pressure P1, the enthalpy at saturated vapor line would be Hg. Okay, so this value we can directly found from here. So H1 would be the this is 2802.6, and the unit is kilojoule per kg. Kilojoule per kg. And at point 2 we have to take the values of Uh, okay, at point 1, we also have to take the values of the entropy. So at pressure P1, the entropy of the gaseous phase Sg is the 6.1243. So S1 is the 6.1243. The unit is kilojoule per kg Kelvin. Okay, at point 2, this is pressure P2, right? So at the pressure P2, which is 0.004 megapascal, the value of the liquid enthalpy is HF is the 1 to 1.39 HF at P1 I would write. Okay, the unit would be same, kilojoule per kg. And the we also have to take the value of HFG, okay, which is the enthalpy difference between the gaseous and fluid phase. Then HFG at for pressure P1, it is given 2432.3 kilojoule per kg. Next, the SF at pressure P1, like here, it is given 0.42239 kilojoule per kg Kelvin, like this value. And SFG, I would write here at P1, it is 8.051 kilojoule per kg Kelvin. Okay, so these are the values I got. And then the values at S2 and S3 we will determine from this data. The liquid and gaseous enthalpy and entropies, we will determine this data. And then this point 4 is at the saturated liquid line at the pressure P1. So this is the pressure P1. The enthalpy at saturated liquid is this, and entropy is 2.7254. So let me write the values here. Okay, so H4 is 1049.8. Okay, I can write the values here only. No, H4 is 1409.8. H4 is the 1409.8 kilojoule per kg, and S4 is the S4. S4 is this 2.7254. 2.7254 kilojoule per kg Kelvin. Now, from this cycle, you would be agree on that, because these 1 to 2 and 3 to 4 are the isentropic processes, means the same uh, uh, entropy at point 1 and point 2, and it would be same at point 3 and point 4. So here I will write S1 is equals to S2 and S3 is equals to S4. Okay, so at S1, Okay. So at S1, the value is 6.1243, and the value at S2 we can write it like as SF at P1 plus X into SFG at P1. Here X is the quality of the steam. We will be able to calculate this X, and based on that we can calculate the enthalpy at point 2. So let me put the values here: 6.1243. This SF at point 1, SF at pressure 1, sorry, the value was 0.4223 plus X into this SFG was 8.051. So from here, the value of x2, I would write x2 would be value of x2 is coming 0.7. Similarly, we will determine the values of x3. So let me write it like this: SF at pressure 1 plus x3 into SFG at pressure 1. Okay, sorry, keeping the same sign convention, it is the pressure 2. Okay, this is the pressure 2. And S4 value we have just written here, it is 2.7254. Okay, so this value is 0.4223 plus x3, this is x2 into 8.051 is equals to 2.7252. From here, the value of x3 we can determine. It would be something 0.28. Okay, so based on this, we can determine the value of S2 and S3. The expression for S2 would be HF at pressure P2 plus X2 into HFG at pressure P2. Similarly, the enthalpy at point 3 would be HF at pressure P2 plus X3 into HF at HFG at pressure P2. Okay, let me write the things here. So, this HF at P2 we have determined. Okay, this is at pressure P2, so at pressure P2, also at pressure P2, pressure P2. Okay, so this value was 121.39 plus x2 is 0.7 into HFG was 2432.3. So this value will comes out to be,
Sir, good evening.
yes, good evening.
What is the significance of X?
The significance is X. It is basically the quality of steam. It can be
Dryness,
defined.
dryness fraction.
Yes, it is the dryness fraction, or we can say the quality of steam. Basically, it is the mass of vapor divided by the total mass. Mass of vapor plus mass of liquid inside the steam.
Yes, sir, okay. Thank you.
Yeah. So at this line from here to here, at this line, the value for x, the value of x would be 1, and on this line, the value of x would be 0. Okay, so now we got the 2.39 plus 0.7 into 242.3. So value of S2 will come as 1824 kilojoule per kg. Similarly, the value of S3 would be 121.39 plus X3 0.28. HFG value is 2432.3. So 28. Plus 0.28 into 52.3. Okay, so value of S3 is coming around 802 kilojoule per kg. So as of now, we got all the values H2, H3, H4, and H1 value was here. Okay, so here it is. So let me write all the values here. Let me take this page upward. Okay, so what was the value of H1? H1 was 2802.6 kilojoule per kg. H2 we have determined as 1824 kilojoule per kg. H3 just we have got 802 kilojoule per kg, and H4 came we found 1409.8 1409.8 kilojoule per kg. So these are the value we got. Okay, and here let me draw the diagram one more time to explain you. This is not correct. This is T, this is S. Okay, all right. So the values would be some here and there in the points. My aim is to just make you understand the procedure. So let me draw these two pressure lines and different pressure processes. Okay, this one I have marked point 1 turbine entry, point 2 turbine exit, point 3 condenser exit, and point 4 the pump exit or the boiler entry. So this is turbine work, this is pump work, this is heat in, and this is heat out. Okay, so now we can find all these values. What would be the turbine work? WT would be H1 minus H2, okay, and WP pump work would be H4 minus H3. Heat supplied would be uh, H1 minus H4, and heat rejected would be H2 minus H3. Okay, so let me put the values next to these also. I'm not writing the things again. I am just taking the values from here. Okay, so I'm putting those values here. So WT would be 6 minus 1824. So this value is the turbine work is 978.6. The unit is kilojoule per kg for all the values. WP would comes out to be H4 minus H3. Okay, so this is my H4, 1049.8. This is my H4, 1049.8 minus H3 value is 802. Okay, so this will come out as some 607.8. Next, heat input H1 minus H4, 2802.6 minus 1409.8, 1392.8, and then Q out would be H2 minus H3, 4 minus 802. This would be 1022. So, like this, you can calculate the things, and also you can have a look at the calculations and how I got these values. So, we got all the things. Let me go to the questions. So, calculate the heat and work transfer. So, like this, we have calculate the heat and work transfer. So, this is answer of question A. Then, what would be the cycle efficiency? Let me write one more thing here. The net work done. W net is equals to WT minus WP, and it would be 978.6 minus 607.8. So 978.6 minus 607.8. Its value is coming around 370.8. If I'm not wrong, 978.6 minus 0.8. Okay. This is the value of W net. Unit would be the kilojoule per kg. Now, in the second thing, they have asked us to calculate the thing, the work ratio. Work ratio, we have defined the ratio of W net by turbine work. So, W net we are having 370.8 and turbine work is 978.6. Okay. And in C part, the specific fuel consumption SSC, we have just learned this would be the 3600 divided by the W net. This W net, this 3600 to convert the kilojoule into the kilowatt hour. So 3600 divided by the W net is 370.8. This is 3. Okay, let me write it again. This is 370.8. Next, the okay. So these are the things they have asked us to calculate, and also the cycle efficiency. Okay, the D part is the cycle efficiency would be the net work done by heat input. So net work done is the 370.8 and heat input is the 1392.8. So let me write these values quickly. 70.8 divided by 978.6. So the work ratio is around 38. Okay. And the specific fuel consumption divided by 370.8, it is around 9.7 kg per kilowatt hour, and the efficiency would be 370.8 divided by 1392.8 into 100. So efficiency I got around 26.62%. So these are the values we had to calculate, and I request you to please check these values because I'm also solving it for the first time. So this is the way we have to get into the things for calculate anything. We just have to determine the efficiency at these 4 points, and then we can calculate anything. So if you are having any doubt in this, then we can take like how we got the values.
Sir, actually, specific fuel consumption 3600. I
Hmm.
can't got this one.
Acha, you
3600.
okay. You can't got this. Let me take another slide. Okay, the blank slide I will. And okay. So you are aware of by the definition of the specific fuel consumption. Okay, you are aware of this definition, its definition. Okay, it
Yes.
tells, yeah, it tells about how much fuel I need to do the per kilojoule of work. Okay, so it is basically it would be the inverse of the net work done. Okay, because this W net, what it is the work done per kg. Okay, net work done is the it is having the unit of kilojoule per kg, right?
Yes. Yes.
So the unit of the SSC would be the inverse of it, kg per kilojoule. Means how
Principal.
much steam I have to supply to generate 1 kilojoule of steam. So kilojoule is basically what it is. Joule is kilowatt second. I can write it like this. What is joule
Okay.
per second?
Okay.
So we can write it like this. Okay.
Now,
So the conversion of kilojoule to kilowatt hour would be the uh, okay, another way. I can write it kilowatt hour, can convert this second to hour by dividing 16 to 60. 60 minute and 60 second, then I am converting this second into hour. So this 3600 coming from here. Okay, when we write when we apply this conversion here, then this would be W net into 3600. Then this unit will be converted kilojoule to kilowatt hour.
uh,
Okay, this
X.
3600, 1 hour consists 60 minute and 67 second. So multiplication of that. Okay, so this is just the unit conversion, nothing else. I hope it is clear, right? Okay, I have to take the another pages for next problem. Okay, next problem. I don't think I have to solve it fully. It is the same problem, but what they are saying is that they are saying the isentropic efficiency for compression and the expansion pressure is 0.75. Then for that we have to determine all the things. This 0.75 is telling that our turbine and pump are not isentropic now. Pump or compressor. Basically for gaseous phase we use compressor, and for the liquid phase we use the pump. Yeah. So let me draw the TS diagram for this. It would be the same problem, only we have to incorporate the turbine and compressor efficiencies. Okay. Okay. This is T, this is S. These are two pressures, P1 and P2. Okay. And our processes. Okay, let me take the another color pen. I will draw the original cycle first, which we have solved. Okay, so okay, this is one, this is two, this is process three, this is process four. Let me write the same values here. Okay, because it is tough to move again and again from this slide to that slide. Okay, I have take this lamp and I will write these values here only. So what we have got, the H1 value we have determined is 2802. I'm not writing the after decimal thing. Kilojoule per kg. H2 was 1824 kilojoule per kg. H3 was 802 kilojoule per kg, and H4 was 1409.8. Okay, 1409.8. It would be the 1410 kilojoule per kg. Okay, so these processes are the reversible process, the isentropic processes. But here they are saying that the our turbine and pump are having the isentropic efficiency of 0.75. So this process would be like this. It won't be the straight line. It would be turned to some increased entropy. Let me write this point as 2 dash. Similar with the pump, this line would be turned somewhere, and let me write this point as 4 dash. Okay, so now my actual cycle would be 1, 2 dash, 3 to 4 dash. These this point 2 to 2 dash and 4 to 4 dash become due to the irreversibility, and where the isentropic efficiency uh, comes. Okay, so we have learned the formula that the isentropic efficiency of turbine is the H1 minus H2 dash divided by H1 minus H2. Basically, it is the ratio of the actual work from the turbine to the isentropic work. Okay, the actual work would be always lesser than the isentropic work, so the isentropic efficiency for the turbine is defined like this. Whereas the isentropic efficiency of for the pump or the compressor is defined as the uh, ideal work which we have to supply to increase the pressure. So it is H4 minus H3 divided by the H4 dash minus H3. Okay, so this is the ratio of the ideal work to the actual work. Whereas in case of the turbine, this is actual work to given actual work out to the ideal work out. Okay, so if you are confused somewhere, so you can think of this is these efficiencies are always the ratio of lower work to higher work. Okay, so the values are given. This eta t is 0.75. I will put all these values here. H1 is 2802 minus H2 dash we have to determine. H1 is again 2802 and H2 is 1824. From here, H2 dash would be so this H2 dash would be 2068 around. I'm not writing the extra thing, kilojoule per kg. And from here 0.75 is equals to H4 is 1410 minus H3 is 802 divided by H4 dash we have to determine H3 is 802. So from here H4 dash would be minus 802. Okay, so this value comes around 1612 kilojoule per kg. So here you can notice one thing. This H2 dash is more than H2, okay, and this H4 dash is also more than the H4. and this comes due to the irreversibility. Next, we can write different heat exchanges and the work done. So these are this actual work done. Here WT would be H1 minus H2 dash. Q out would be H2 dash minus H3. This pump or compressor work would be H4 dash minus H3, and this heat supplied would be H1 minus H4 dash. So now, can you write all the things here? Okay, let me write all the things here. So WT here is H1 minus H2 dash 2802 minus 2068. It is 740. Pump work is H4 uh, dash minus H3 here. H4 dash 1612 minus 3802. This is 810, and Q in is H1 minus H4 dash. So it is 2802 minus H4 dash is 1612. This is 1190, and Q out is simply the S2 dash minus S3. S2 dash is 26068 minus 802. It is 1266. So here I am having all the values. Okay, and similarly I can calculate the things which I have calculated in the previous problem. Okay, so let me write the formula here only. Here W net, I also can calculate WT minus WP. It would be P minus. Good. So this thing I need, you have to check WP H4 dash 1612 minus S3 is 80210. So these values would be around, and these are not correct. Only you have to focus on the uh, how I have done these things. Okay. So in the process, if you have any doubt, then we can take that. Otherwise, we will move forward. Okay, then come to the second lecture, modeling of the Rankine cycle, then ideal Rankine cycle, irreversibility and losses. Sorry, we are not having time for that. Okay, then we can solve this quick problem if you would allow. Okay, you are having any doubt?
So theory person,
Uh, you want me to explain the theory portion?
yes.
Okay, so starting with the modeling of the Rankine cycle, uh, what uh, we have done. Okay, so here we have started with the Rankine cycle. Uh, till, till now we have done with this Carnot cycle,
Not say.
and also we have learned that Carnot cycle is not feasible in the vapor applications. So we have moved to the Rankine cycle. Okay. So Rankine cycle is nothing but in the Carnot cycle we are having two constant temperature, and here we are having two constant pressures and two constant uh, uh, entropy, means two isentropic processes. Let me draw two pressures here. These are the lower pressure, say upper pressure, and the constant pressure lines goes like this. By this thing you would be familiar. The constant pressure lines on the TS diagram goes like this. Okay, so in the Carnot cycle, what we have seen, it ends here only because it is the constant temperature process for that. But in the Rankine cycle, we can move to the higher temperatures. Okay, along this constant pressure line. So, like this point could be my turbine entry point in the Rankine cycle, so that the work ratio would be increased, and we can expand it like this, point 1 to point 2. And here my condenser can condense the steam to the saturated liquid, and here a pump would be introduced, and from here to here the boiler thing would be go. So point 1, point 2, point 3, and point 4. Vis-a-vis, if we were in the Carnot cycle, the cycle would be like this only. Okay, so comparing the Carnot and Rankine cycle, this is my Rankine cycle work, the turbine work in the Rankine cycle, and this is the turbine work in the Carnot cycle. Simply you can see that this Rankine cycle work would be much higher than the Carnot cycle work. Okay, and this is the pump work in the Carnot cycle, and this is the pump work in the Rankine cycle. So pump work in the Rankine cycle is also reduced than the Carnot cycle, and the turbine work is increased than the Carnot cycle. So the work ratio in the Rankine cycle is increased. That's why we have moved to the Rankine cycle. Then next thing we have seen the effect of the boiler pressure and the condenser pressure on the vapor power cycle. So next, let me quickly do this. We are actually running out of time. Effect of the, okay, it is next. Okay, the effect of the boiler and condenser pressure. So this concept we will learn here. Sorry about my drawing. I will make two TS diagram here. T S and S. This is the vapor dome. This is the vapor dome. And let me make the two constant pressure lines like this. It would be something like this. Okay. Okay. So first we will see, this is the boiler pressure. This is the condenser pressure, boiler pressure and the condenser pressure. Okay. So let us suppose this is our original cycle. This is our original Rankine cycle. Point 1, 2, 3, and 4. Okay. So what we have done? We have increased the boiler pressure. Increase the boiler pressure PB. So we have increased it to this point. Okay. What will happen? This point will come like this. So what will happen? This point 1 will shift to here. This is earlier point 1. This is point 1 dash. And this point 4 will shift to here. Okay, by increasing this boiler pressure. So earlier we were getting the turbine work like this, and now we are getting the turbine work from here to here, WT dash. So clearly we can see 1 dash, the height of this 1 dash to 2 is higher than 0.122, so that WT dash is greater than WT. Okay. Next, the pump work is also increased. Okay, this point 4 moved to the point 4 dash, so that my pump work is also increased the earlier pump work. But this increment is far lesser than this increment. Okay, the as you can also analyze from here, this increment is much more than this increment, so that overall work ratio would be increased and the efficiency will also be increased. So we can say by increasing the boiler pressure, my work ratio and the efficiency would be increased. So this was one thing. Second thing, increasing the condenser pressure. You
Sir,
want to
what?
ask?
Sir,
Yes. Yes.
uh, sir, boiler pressure is constant.
Yes. Boiler.
Rated boiler pressure. Some of boiler pressure is rated 170 kg pressure.
Okay.
Oh, how we increase the boiler pressure against the design value?
No, we can't design, we can't increase the boiler pressure above than the design point. Here we are talking about another boiler. Means simply we are seeing the effect of
Ideal case.
if we will increase the uh, boiler pressure by using different boiler or so, what would be the effect on our work ratio and the efficiency. So here we have seen that if we use the boiler which has higher rated capacity, then in that case our efficiency and work ratio would be more. Only this conclusion we want to draw here. And second thing, the effect of increasing the condenser pressure. So this is the condenser pressure. So if we will increase the condenser, we will decrease the condenser pressure. This line will go like this. So earlier, if we are getting this much turbine work, and now we will get this much of turbine work. So this is the increment in the turbine work, and this would be the increment in the pump work. But this turbine work increment would be far more than this, so that in this case also work ratio and the efficiency would be increased. So our aim is to run the plant as high as as possible by boiler pressure and as low as possible condenser pressure. So these are two design aspects. And I don't know more than that we have covered in these lectures. Yeah, the effect of boiler and condenser pressure. Then irreversibility losses. Uh, the same thing which I have shown you, which we have used the turbine and boiler, the turbine and compressor efficiencies. This is H1 minus H2 divided by H1 minus H2 dash like this. This is my isentropic process and this is the ideal process like this. Okay, this is my point 1, this is point 2 and this is 2 dash. This is isentropic and this is the actual. So H1 minus H2 divided by H1 minus H2 dash, these things we have looked into. Also this pump thing. Okay, uh, okay, let me don't be in hurry. Let me make the things more spacious. Okay, so these are my two presets, P and S. Let's suppose this is the ideal cycle. This is my ideal cycle 1, 2, 3, and 4. By the introduction some irreversibility and losses, these isentropic processes wouldn't be like this. Some entropy would be increased and the process would be like this only. It's not compulsory that uh, it would be limited to this line. It can go beyond this line like this. Okay, this would be 2 days and this could be my 4 days. So the isentropic efficiency of the pump would be, as I have earlier written the things, H4 minus H3 divided by H4 minus H4 dash minus H3. This is ideal work which turbine should give. This is the actual work. This is the ideal work H4 minus H3 which the ideally pump should take consume or what it consume more than that which is H4 dash minus H3. So these are the things only. Okay, so we are left with half an hour. You want me to solve this problem or you can solve
Okay, sir. I will solve this.
you can try this na? Hello,
Yes.
or you
Yes,
want me to
yes, sir.
solve? Okay, okay. So please try this problem. If you are any, if you will have any doubt in this, then we can take that in next class. So here, this is the simple problem. Similarly, the we have done the last problem. Okay, so I have provided the steam table here. And one more thing, you also have to check if
Yes.
I have done any mistake in the last problem. The procedure would be the same. And here they have introduced this isentropic efficiencies
Efficiency.
of the pump and the turbine.
Yes.
So you have
Yes.
to use this formula and calculate the H1, H2 dash, H3 and H4 dash. And if you will face any problem, you can mail me. I will provide you the solution or we can discuss in the next session. Next, the compulsory
Yes.
thing. Let me solve this assignment problems for you. Okay, so we will do it quickly. It is also having some numerical problems. So the process associated with ideal Rankine cycle. What is this? We have learned. that the ideal Rankine cycle is having two constant pressure and two isentropic process TS. Okay, so the option D would be correct, two constant pressure processes and two isentropic processes. While in the Carnot, we were having two constant temperature and two isentropic processes. So option D here would be correct. Next, if the heat sink temperature is decreased, keeping other parameter constant, the thermal efficiency of the Carnot engine, what would be? So, what they are asking the same thing which we have done. Basically, they are decreasing the sink temperature means they are decreasing the condenser pressure. Okay, so this thing we have seen, like by decreasing the condenser pressure from here to here, the WT more increase and WP would be less increase. So the work ratio would be increase and the thermal efficiency is increase. Thermal efficiency is also increase. Okay. So option C would be correct here. Okay. So in third problem, okay, a Carnot engine operates between the temperature limits of 227 and 127 degrees centigrade. If the work output is 10 kilojoule, then the amount of heat rejected would be. This is a very simple problem. Okay, first we have to convert these temperatures to the Kelvin, as we can put only the Kelvin temperatures. So 227 plus 273, 500 Kelvin, and this would be the 400 Kelvin. Okay, so it is given that my source is at 500 Kelvin and sink is at 400 Kelvin, and the work output, this is engine work output is 10 kilojoules. Okay, so what they have asked then the amount of heat rejected. What would be the amount of heat rejected? So this is Q in, Q rejected. They have asked for this. So the efficiency of Carnot engine, we know efficiency of Carnot engine 1 minus the sink temperature divided by source temperature. Also, it is equal to W net by heat supplied. So we will put the values here. 1 minus 400 by 500 is equals to W net. They have provided 10 kilojoule and Q in. So from here we can determine the input heat. This thing I have determined, it would be the 50 kilojoule. We know that the heat rejected would be inlet minus W net. Okay, as we can see from here, the energy balance is Q in is equals to W net and some heat is rejected. Okay, so from here 50 minus 10 is equals to 40 kilojoules. Okay, so this C option is correct. Next, the work ratio of a Rankine cycle is higher compared to Carnot cycle under the same pressure limits. So this option, this statement is true, as we have seen that while switching to Rankine cycle from the Carnot cycle, the work ratio is increased. However, the efficiency is decreased. But here we want more work, so we use the Rankine cycle only. Even the Carnot cycle is not feasible. We are having a number of reasons as we have learned and we have seen in the previous lectures. Next, the primary objective of condenser in a steam power plant is to increase the turbine exhaust pressure. Okay, increase or decrease. The condenser is used to decrease the turbine exhaust pressure here. To decrease, we don't want to increase the turbine exhaust pressure. The this uh, pressure of the condenser is very less, and it is used to decrease the turbine pressure. So this is statement is false. Hope this is clear. It is not very big problem. Next, problem number 6. Okay, so in the Rankine cycle for a steam power plant, the turbine entry and exit enthalpies. Okay, so here the enthalpies are given directly. Okay, so here we are having nothing to worry. Okay, so like this in my Rankine cycle, P and S. Here direct values are given. This is turbine entry, turbine exit, condenser exit, and pump exit 1, 2, 3, and 4. So what they have given enthalpy at turbine entry. This is your H1. Okay, let's not make it messy. So H1 is 2803.4, H2 is 1839.9, respectively. The enthalpies of water at pump entry and exit. So where is pump entry? This is point 3 is pump entry. Okay, so S3 is 811.15, and H4, the pump exit is H4. H4 is this, H4 is 141049.8. What they have asked? They have asked for the specific steam consumption in kilojoule per kilowatt hour. So nothing to worry. The specific steam consumption in kilowatt hour would be 3600 divided by W net. Here W net would be Wt minus Wp. Wt is H1 minus H2, and Wp is H4 minus H3. You just have to write the values like this. H1 minus H2, 2803.4 minus 1839.9 minus H4 is 1049.8 minus 811.15. I have determined these things. So W net would be here 724.85 kilojoule per kg. So specific steam consumption would be 3600 divided by 724.85. Okay, and the value will come out to be 4.96, around 4.96 kg per kilowatt hour. So this value would be 4.96. Okay, so this is very simple problem. You don't even have to look at the steam table. Then next, in the Rankine cycle for a steam power plant, the same values are given, I think. 2803. Yeah, the same values are given here. Okay, where it gone? Okay, so in problem 7, the same values are given. This H1, H2, H3, and H4. What we have to determine? We have to determine the back work ratio. We have defined the back work ratio as the pump work divided by the turbine work. Okay, and here the pump work is H1 minus H2. Sorry, this is the turbine work. Pump work is H4 minus H3 and the turbine work is H1 minus H2. Okay, I will write the values here. 1049.8 minus 811.15 divided by H1 is 2803.4 minus 1839.9. So this back work ratio will come out to be around 0.2476. Please check the values. Okay, this is 0.2476 like this. Then next is 8. In the Rankine cycle, the saturated uh, vapor or steam enters the turbine with a mass flow rate of 80 kg per second. So this is, I think, quite lengthy problem. Let's see. So here the mass flow rate of steam is given. Okay, it is 80 kg per second. 80 kg per second, and it enters the saturated vapor in the turbine. So the entry point is this. Okay, so entry point is this 2, 3, and 4. This T and this is S. All right. So here the thing is given. The work done by the pump is 10 kilojoule per kg. So here pump work, which would be eventually H4 minus H3, it would be the 10 kilojoule per kg. Okay, and the back work ratio they have provided, back work ratio, which is the pump work divided by the turbine work, it is 0.008. So from here we can determine the turbine work. Okay, and they have given the thermal efficiency of the plant is, I should write thermal efficiency TH, I would write, is 0.4%. So first what they have asked, the work output from the turbine. It is simply the back work ratio, which is the ratio of the pump work or to turbine is provided. So pump work is 10 divided by WT would be 0.008. So from here, WT would be 10 divided by 0.008. It would be 1250 kilojoule. Okay, it would be the. So from here, I don't know you have noticed or not. You can see that here pump work is only 10 and the turbine work is 1250. Okay, so you can see the difference. And when we increase the boiler pressure, like here, and the condenser, we decrease the condenser pressure like this, so that the change in this pump work is very less. Okay, and also it is having very low magnitude, but the change in this turbine work is uh, very high. So in the Rankine cycle, what we have seen, we have decreased the pump work significantly than the Carnot cycle, so that the work ratio is significantly increased. Okay, this is the advantage here. The pump work is almost negligible than this turbine work. Next, what they have asked, they have asked the work ratio. It is nothing but the work ratio is the net work divided by the turbine work. The net work uh, we are having the turbine work minus pump work divided by the turbine work. So in one way we can do it like this: 1250 minus 10 divided by 1250. This value will come around, would be 0.992. Okay. Okay, yeah, 0.992. So here we can see that the work ratio is almost unity. Okay, the pump work is very less. So this would be the answer for the problem 9. Next, the heat transfer rate into the working fluid in the boiler. This thing we have to determine. We know that the thermal efficiency is the net work done divided by the heat in. Okay, if I have done something wrong. Okay. I have done one mistake here. Not the mistake. This is just the extension. Okay. Actually, this work we have to determine in the megawatts, and here we have determined in the kilojoule. So WT total would be the mass flow rate of steam. This is kilojoule per kg, and the WT. So this value is given 80 into 1250. The unit will be kg to kg cancelled. Then okay, the unit kg per second into kilojoule per kg. So from here kg to kg cancelled, kilojoule per second would become kilowatt. Okay, here you have any doubt how the unit become kilowatt? Okay, but they have asked in the megawatt. So to convert into the megawatt, I am dividing it by 1000. So that unit would become megawatt, and this value would be this value would be 100 megawatt. Okay, so I'm sorry, I have calculated in it in the kilojoule, but because here the mass flow rate of steam is provided, we can also calculate in the megawatt. The work ratio calculation is correct. It would be the 0.992. Then we have to determine the rate of heat transfer into the working fluid in megawatt. Okay, so the thermal efficiency is provided 0.4. The W net we have just determined. The work output from the turbine is 100 megawatt. So W net we will determine first. Okay. W net is equals to W turbine minus W pump. Okay. 40, 1240 kilojoule. Okay. So 0.4 is equals to 1242 divided by Q in. So Q in from here it is 3100, but in kilojoule. To determine the values in megawatt, put it as I have determined by the mass. I have to multiply it by the mass flow rate of the steam into the value in kilojoule into 10 to the power minus 3 to convert the units into the megawatt. Okay, so this value will come 80. Okay, the value was 80, right? Yeah, it is 80 into 3100 into 10 to the power minus 3. So Q in dash would be 248 of megawatts. Answer would be 248 megawatts. Okay, so these are the 10 problems I want to discuss in the last. If you are having any doubt in these problems, then we can discuss. We are still having 8 minutes.
Okay, sir. Thank you. I will try this problem.
Yeah,
After this
please.
next
Yeah,
session, I will discuss.
yeah, please try. Till then, I will also keep the solutions ready, and yeah, you can also mail me if otherwise
Okay, sir.
on the next Friday we can meet. We meet, and then yeah.
Okay,
So
sir. Thank you, sir.
that's it. Thank you for joining. Okay. Good night.
Okay, sir. Thank you, sir.